And then we have Joris de Grote from Ghent University. Please go ahead.
Thank you for the introduction. So indeed, thank you all for staying here. This is joint work together with Thomas Haas and Niels Bernhard, who already presented yesterday, and our thesis students. It fits within the Born project, which is a Belgian project together with UC Louvain from Professor Winkelmans. So in this presentation, I want to show how we predict the performance of airborne wind energy devices. And we want to do that starting from the design. So we just get a plan form of a device where we get the profiles and the chord lengths and how they vary over the span of the device. We want to include the controller as well, because it's so important in airborne wind energy. It's not just straight level flight, but all kinds of flight patterns. We want to respect stress constraints because you can put as much force on the device as you want, but at some point you're going to break the wing, and so you should avoid that you overstress the wings. And also, we want to be able to combine multiple devices, so not just one airborne wind energy device, but a multi-kite combination or a combination of an airborne device with a conventional wind turbine. So we want to combine it with other things. So if you have all these goals, then we need to take that into account in the software that we're using for the aerodynamics. So if we want to start from a design, any design that you give us, then we need good meshing tools and a feasible approach to mesh the entire device, starting from the geometry. We need to handle the rigid body motion to follow the trajectory prescribed by the controller. And we also need to take into account the motion of the control surfaces affecting the aerodynamic forces. When you want to respect the stress constraint, you need to be able to calculate the deformation and the effect of that deformation on the aerodynamic forces. And to combine multiple devices together, you need modularity. So those are a lot of requirements for the aerodynamic force evaluator. And we think that we can satisfy all of them by using a combination of the overset approach and the arbitrary Lagrangian-Eulerian formulation. So this overset plus ALE combination is very powerful in our opinion. In the overset approach, we take a big box, a big Cartesian grid for the background domain, so where the bulk of the wind flow is simulated. And then on top of that, we put component meshes around the wing, the control surfaces, and so on. So it's an overlapping technique with multiple meshes. The ALE formulation is then used to handle the rigid body motion of the aircraft, the deformation of the wings, but also the motion of the control surfaces relative to the aircraft. Just to give you a short explanation of the overset approach and the ALE approach, let's start with the overset now. Here you see a mesh around, a component mesh around the main wing of the MegaWest device, because that's the one I'm going to use in most of the explanation here. As you can see, it's a typical C mesh around the wing. And so it's a block-structured mesh. A two-dimensional cross-section is shown in the figure, and it's extruded basically in the span-wise direction. A typical resolution that we have used is 60 cells in the chord-wise direction, 38 in the radial direction, and about 70 in the span-wise direction, giving a total of 2.6 million cells for the wing, for the component mesh of the wing, and about 7 for the background domain. You also see a histogram for the Y+ values, because we typically do unsteady runs simulations, where you see that the Y+ is in the typical range for wall functions in an unsteady runs simulation. So to make meshes like that, Thomas developed a meshing tool that if you give it a chord and a span-wise distribution, it can make a block-structured mesh for the component. Of course, you have the component mesh close to the wing, but then you have the background mesh for the bulk flow, and they need to exchange information. And that is done by the overset technique. In the background mesh, which you see on the left-hand side, you actually make a little hole where it's being overlapped by the wing. And around that hole, there are blue cells, and that's where you impose boundary conditions, let's say, about the flow close to the profile. the information for those boundary conditions is coming from the red cells close to the profile in the component mesh. On the other hand, in the component mesh, that's for the flow close to the device, you need information about the flow further away from the device, and that is being imposed in the blue cells over here at the outer boundary of the component mesh, and that information is coming from the red cells in the background domain. So you interpolate in both directions, and there is some overlap between the component mesh and the background mesh. Those interpolations, they are done in an iterative way, so information is exchanged between the background and the component, and you have to make sure that in the regions where you do the interpolation, the mesh sizes are similar, otherwise your interpolation quality will suffer. And especially if you have rigid body motion, you have to take into account that your time step is not too large. Because in green you see the background mesh of a certain time step, within white a little hole, that's where the wing was in the previous time step. If you then move the wing, or the kite, then you see it's no longer overlapping with the gap from the previous time step, but it's possible that the blue cells here, where you need to get some information from the background, start overlapping with the hole from the previous time step, and then the interpolation doesn't work properly. So you need to choose your time step wisely, or alternatively, you have to make the component mesh bigger, and then you also can take bigger time steps. But then the computational cost also goes up, because you have a bigger region where you have both the component mesh and the background mesh. So that is also a double computational cost there. Okay, so enough about the overset approach. The ALE formulation is then what allows us to handle the rigid body motion and the deformation in the component mesh. Let's have a look at some part of the fluid domain. So you see the mesh there, and in gray that's some fluid, some air. The red line indicates the structural boundary, so that's where the wall is. And if you perform a time step with rigid body motion or deformation, the wall will move. In a purely Eulerian framework, that doesn't work. The fluid will start moving through the wall of the Eulerian grid, so that's not a good idea. In the Lagrangian approach, the grid moves along with the fluid. In some situations that works, but if you have a complex fluid flow, the grid obviously cannot follow for a very long time. It will be completely tangled up. So instead we do something in between. That's the ALE approach, where at the wall, the grid cells, they follow the structural motion, but in the rest of the domain, the grid is moving in an arbitrary way as the user wants it, typically in a way such that the grid quality is preserved. And you see here, we keep a good orthogonal quality. The grid lines are orthogonal, so they definitely don't follow the fluid. They are just there to follow, to keep a good grid quality. So in the ALE approach for the deforming fluid domain, for the component meshes, we will move the grid according to the structural motion, at least in the normal direction on the interface. And in the rest of the fluid domain, inside the component mesh, we will do an arbitrary extension of the interface motion to preserve the grid quality, resulting in a grid velocity that needs to be taken into account in the fluxes in the component meshes. So after that introduction of the ALE approach and the overset approach, let's have a look at some results. First, how we handle the deformation. Here I present a result obtained by Niels, where he coupled the overset ALE flow solver with a finite element solver using our in-house coconut coupling tool. And that yielded the wing deformation of the MegaWis device during a circular flight. And as you can see, the left wing and the right wing, so here the wing tips, they have a different deformation due to their different velocity. And we can calculate that deformation with a uniform inflow, that's the blue line, but also with a logarithmic inflow. And then you see for every flight cycle, the wingtip goes up and down and is different for the left wing and for the right wing. So we can handle deformation with this overset ALE approach. We can also handle control surface motion. To do that, different C meshes were created around the rudder, the elevator, the ailerons, the main wing, and they were all overlapping, and they were moving as one rigid body in the background domain, but they could also move relative to each other. So we can handle the rigid body motion of the rudders, the elevator, and so on, and then calculate the forces in the different directions. You see here X, Y, and Z direction as a function of time, where X, Y, and Z are also indicated in this figure for a certain trajectory, with in green a real out phase and in red a real in phase. So it has a logarithmic profile here. And you can see if we include the control surface motion, then the forces are quite nicely matching with the ones predicted by Auebox. And Auebox was used to generate the trajectory in the first place. So the control surface motion can be included in these simulations. Now, I told you about combining it. So maybe you have heard about this patent where you can put airborne wind energy devices on top of wind turbines to create three-dimensional wind farms. So a lower layer with wind turbines and airborne wind energy devices at higher altitude. We have studied something like that in a master thesis last year, where we put here a wind turbine. That was a 5 megawatt wind turbine. Then an airborne wind energy device behind it, intentionally flying through the wake of the wind turbine, and then looking at the wake further downstream. All of this was done with an ALE overset approach, where we have 3 wind turbine blades rotating in a background domain, and then the main wing of the MegaWest device flying a circular flight trajectory through the wake of the wind turbine, as you can see over here. And so you see the 3 wind turbine blades on the left-hand side, and then the MegaWest wing flying through the wake of that wind turbine. And we can look at the turbulence intensity as a function of the height at different positions downstream to see what the potential effect would be on a second device, on a second wind turbine further downstream, for instance. So we can combine an airborne wind energy device with wind turbines, but also we can combine different airborne wind energy devices. So there is modularity of this approach. In a current study, we are combining 3 MegaWest wings, so 3 different component meshes which are overlapping with one big background domain to simulate what a multi-kite system is doing, and so to replicate this situation, for instance, over here. So all in all, we come to the conclusion that the combination of an overset and an ALE formulation is a very powerful tool for the prediction of the aerodynamic performance of airborne wind energy devices. If you want to start just from the design, from the drawings, from the plan form and the profiles, if you want to include the controller in the performance evaluation, even the deformation of the wing to make sure that you don't break the wing, and if you want to go towards combinations of multiple devices, multiple combinations with wind turbines or multiple airborne wind energy devices together. But unfortunately, there is no free lunch. That only exists at conferences. So you have to pay a price, and that's the iteration between the different grids. It's also the interpolation, so it has an increased computational cost compared to just a single grid. In ongoing studies, we are increasing the fidelity of the turbulence modeling, and we are going from U-runs to hybrid runs LES techniques. That's the work of Thomas. We are going towards multi-fidelity simulations, and we are coupling with control. That's what Niels is doing, especially looking at Auebox as controller. So with that, I'm ready with my presentation. And I give the floor back to you.
Thank you very much, Joris. Impressive work that you do at the University of Ghent. Are there any questions? Was very clear. I think then thanks again.
You're welcome.
And